Hello to anybody who's already logged in. We're just gonna give one more minute until we're right on the dot before we start. Okay. Hello, my name is Alexandra Kidd, and welcome to Interface Engineering's 2025 Educational Webinar Series event. Today we have Wind, Sun, Sand, and Salt, Not a Day at the Beach for Designers. Thank you everyone for logging in to join us for this. Today's presentation will be recorded and made available through our website. All audience microphones will be muted during the presentation. However, you can ask questions in the question field, so please do not hesitate to do that. Interface Engineering is an approved AIA CES provider. For today's participation, you will earn 1 learning unit. All attendees will either receive a course completion certificate, or if we have your AIA number, which you would have submitted along with your registration, attendance will be reported for you to AIA and you'll get a notification within 2 weeks. We will leave 10 to 15 minutes at the end to answer any questions that come up. If we do not get to some of them, we definitely will distribute a summary of all of that information with comprehensive answers. And now I'm going to go ahead and turn it over to our Managing Principal, Roger Frechette, and Associate Principal and Senior Mechanical Engineer, Keith Pasma, to get us started.
Alexandra, thank you very much. Yes, good afternoon. My name is Roger Frechette, and I'm joined today by my partner, Keith Pasma. I am a mechanical engineer with nearly 40 years of experience. And before we jump into the actual presentation, I just wanted to tell you a little bit about our firm, Interface Engineering. We are a firm that was started in 1969. Our work covers a very large selection of market sectors, everything from science and technology to aviation, hospitality, and other. The design services that we provide include mechanical, electrical, plumbing, fire protection engineering is our base, but we also provide building services modeling, energy modeling, lighting, daylighting, building technologies, and building commissioning services. Perhaps we're best known for our work in sustainability and high performance design. To date, we've designed more than 260 LEED certified projects, 85 of which have achieved a platinum level. We are experts in net zero energy design, have completed 85 net zero energy projects, 17 living buildings, 4 carbon neutral buildings, 5 well buildings, and 5 green globe buildings. So our offices are located across the United States. In total, we have 10 offices. Our work, ongoing work, right now we're currently working in 45 of the 50 US states. There's 5 that we're missing. So any architects on the call, we could use your help finding some projects in those last 5 states. We are also an international practice. We are currently working in 95 countries. So as Alexandra mentioned, whether you're using the web version of GoToWebinar or the standard desktop version, both versions have the capability to log questions into the questions portal. We recommend that you do so, encourage you to do so. We will leave 5 to 10 minutes at the end of the webinar to answer those questions. And if there's any questions that we don't get to in the time allotted, we will record the questions and answers and distribute them to all the participants on the call today. So without further ado, jumping into The topic, the course description today, this webinar explores the unique challenges of designing building systems in coastal and island environments where salt-laden air, high humidity, and extreme weather demand more resilient solutions. You will learn about the 8 S's that define the conditions in many of these regions. You will learn how to apply best practices to create systems that stand up to the elements, optimize performance, and protect long-term investments. So the learning objectives: 1, to gain an understanding of what defines a coastal climate from an energy code and mechanical design perspective. You will learn about common pitfalls and solutions for designing mechanical systems in coastal climates for both architects and engineers. You'll learn about designing around extreme weather, seismic events, even stack effect conditions and hot coastal and island locations, and understand limitations of certain materials in coastal and island climates. So the 8 S's, hopefully this will be the big takeaway. If you learn the 8 S's, you will be well equipped to tackle design for any project and these types of climates. So surf, sand, sun, salt, sweat, strong winds, shaking, and stack effect. Those are the 8 S's. So going through each one, first just talking about surf and water intrusion. So start from a high level, from a planning perspective. Good planning goes a long way in protecting buildings, building structures, and infrastructure from the impact of storms, storm surge, flooding, sea level rise. So the Federal Emergency Management Agency, FEMA, maintains and updates. Oh, wait a minute. I'm sorry. Lost my place in my notes. There we go. Sorry. Most coastal communities employ comprehensive strategies to mitigate the impacts of coastal flooding, sea level rise, and storm surges. So a typical coastal flood master plan will include hazard assessment, a vulnerability assessment, resilience initiatives, project development, and critical structures. And environmental justice analysis. So there we go. So the Federal Emergency Management Agency, FEMA, maintains and updates data through flood maps and risk assessment. So FEMA's Map Service Center is the official public source for flood service information. So these maps that FEMA develops show the locations of the 100-year floodplain. Now, buildings can be built within this 100-year floodplain, but they must be elevated above what is known as the flood protection elevation, or the FPE, which most jurisdictions set as being 2 feet above the 100-year line, or what is also known as the base flood elevation, or the BFE. So these buildings within the floodplain are also, that floodplain is also known as the Special Flood Hazard Area. A lot of acronyms. The SFHA are required to be built with what is known as flood vents. So you see in the middle of this image, a little square down at the base called a flood vent. So the reason for these vents is to control hydrostatic pressure. So if a structure was built with open space, crawl space, storage areas, or air cavities, and did not use the flood vents, then what would happen during a flood is that water would rise up the exterior side of the foundation walls, but it would not fill on the interior. That would result in a static pressure differential from inside to outside. This pressure differential could easily damage or destroy the foundation wall. So with the flood vents, water is purposely allowed into that space within the building, under the building, and helps to eliminate that differential, helps to balance that differential. So when the pressure is equalized, interior finishes may be sacrificed, but the overall building structure can be saved. So drainage considerations. This image, this is one of FEMA's 100-year flood maps as for the city of Alexandria, Virginia. This particular neighborhood is very familiar to me. My office was essentially right there at the corner of King Street and Union Street, shown on the image on the right. And this area is flooded about once a year on average. It is down within that 100-year floodplain. This waterfront area is very prone to floods. Now, the floods in Old Town, they occur as a result of the Potomac River overflowing, and that can happen due to heavy rains, where rains fall in the west and run down the hill towards Alexandria. Strong winds from the south can cause flooding. Snow melting can cause flooding. Even full moons and moon tides can cause the flooding, or any combination of any of those elements. So they are used to the frequent flooding. So Alexandria, like many older cities around the United States, along their waterfront areas, also have older infrastructure, older sewer systems, older storm systems. So in many places within the city of Alexandria and Washington, D.C., and again, many older cities, you'll find that the storm systems and sanitary systems are combined. It's one system. And what happens with these combined systems is when you have the heavy rain or storm surge or flood event, these combined systems easily overwhelm the city infrastructure. That excess water cannot be handled by the systems provided, so they overflow, and they overflow into the waterways. And when that happens, they create a real potential for health hazards. So newer municipal drainage systems, they've learned their lessons from that. Newer systems tend to be separate, where the wastewater stream is an entirely separate distribution system from the stormwater drainage system. And this prevents that sewer water from contaminating the waterways. However, you get into these regions, it is impossible to completely separate the buildings from the water. And when water does make contact with the buildings, it's important that these buildings are designed to do the best that they can to insulate themselves from the water intrusion. So therefore, the buildings in these wet areas must take steps to enhance the building envelope. So this slide right here is one example showing a few examples of what additional protection can be provided, such as damp-proof membranes, moisture-resistant plaster, mold-resistant paint, etc. So there was a gentleman by the name of Gilbert White. He was a prominent geographer, and he once said, "Floods are an act of God, but flood losses are largely acts of man." Something to consider. So next of the 8S's, talking a little bit about sand. So sand can have a significant impact on equipment located in or around a building, on top of a building. So sand, especially the silica type of sand, the sort of sharp stone elements within sand, can cause abrasion, erosion, contamination, leading to reduced lifespan, increased maintenance, and potential downtime. Sand can enter moving parts when mechanical systems rely on lubrication. That sand can get into the lubrication and affect bearings, hydraulic systems. It mixes with the lubricant, leading to increased friction and wear. And that wear can then lead to oil leaks, damaged gears, bearings, damaged seals, and eventually a catastrophic failure. So the images here on the screen, this is a somewhat of an extreme example of when this happens. A couple of years ago, I was invited to travel to Khartoum, Sudan. They had a hospital there that had experienced significant sand damage. They had outside air intakes that were not properly treated. They had mechanical equipment designed and exposed on the roof. So the building experienced significant sand infiltration. And as a result, much of the major healthcare hospital equipment was damaged beyond repair, and much of the building's HVAC system was also unusable. We had worked closely with the hospital to develop a plan to repair what we could and replace what needed to be replaced. Unfortunately, before that project was able to get started, civil war broke out, conflict between the Sudan army and the rebels, and the hospital was burned to the ground completely. It destroyed. Very unfortunate. So some of the things that in new design that need to be addressed, this equipment, major mechanical equipment must be indoors, must be separated from areas where they can be impacted by the sand intrusion. That's probably the major strategy. Next slide. That said, all buildings, all occupied buildings need to pull fresh air, ventilation air into the building. And it's very important to properly treat these outside air intakes. So this image shows an example of a sand louver. So the way they're designed, air passes through, it actually drops the pressure and velocity of the air in the middle of the louver, and the sand then falls out of its solution with the air and can be extracted from the building. The reason designers need to pay really close attention when they use these sand louvers is they're very sensitive to air velocity. And this image demonstrates that. When you design this particular sand louver to operate with 0.5 meters per second air velocity entering it, it's very effective. 88% of all the sand particles will be removed from the air. However, if that air velocity, if that is allowed to increase up to 2 meters per second, its effectiveness drops from 88% all the way down to 5%. So the only way to keep that velocity low is to have large louvers. So these sand louvers tend to be significantly larger than conventional air intake louvers. That needs to be accounted for in the building's envelope design. So with that, I will hand it over to my partner, Keith Pasma. Keith?
Thank you, Roger. Allow me to reintroduce myself. My name is Keith Pasma, Senior Mechanical Engineer and Associate Principal, currently residing in the 9th Island of Las Vegas. So how's it to all of my friends joining us from down in Hawaii? Now, on to the star of the show, and I'm obviously talking about the sun here. And it's the sun which really brings us down to these tropical regions and these coastal climates to begin with. And when we're down in these areas, we always have to remember to put on sunscreen. People think they get sunburned from losing track of time because they're having too much fun, but realistically, it's a combination of this and the UV rays that are much more intense down in these southern regions. You can see here on the right side of the screen, the UV index as it compares to the rest of the world. And you can see as you go further down into tropical areas like Hawaii or the Caribbean, it's much more intense. So if it's much more intense on us, that means it's also much more intense on our building materials. You can see here some examples of some UV damage and typical UV damage on various building materials. On the left here, you can see 2 EV charging stations, which were recently installed in a project we're working down in the Caribbean, the Cayman Islands. You can see the one on the left is shielded by a overhead PV array, and it's looking pretty much a new condition. And the one directly to its right is one that is not. And you can see it's already starting to color and start to degrade. Anyone who's left out a Home Depot bucket or Lowe's bucket outside on their back porch or lanai can attest to how quickly those things will disintegrate the next time you try and move them. Other typical things you see here are PVC piping, typically used in pools, and the classic refrigerant insulation over piping. Damaged here both by UVs and probably by birds. So what can we do to protect our materials? Well, for one, we can choose materials that are more resistant to UV rays. We can select CPVC or UV resistant PVC. Now, for items that can't be selected of a material that is more resistant, we should cover and protect them. We can cover these items with jacketing. You can see here on the bottom left, most refrigerant equipment manufacturers will suggest some form of UV jacketing. That'll go over their insulation. And then if you need something a little bit more robust, you can use something like aluminum cladding, which will provide a much more long-term solution for your insulation. Now, nothing like sitting on the beach in the sun, and there's nothing like sitting on the beach under an umbrella in the sun. And our buildings feel the same way. We were lucky enough a couple years ago to work with the Department of Education down in Hawaii to study heat mitigation strategies for some of their buildings. And this ranged from things like painting their buildings white for reflectivity, as well as studying their overhangs. You can see here how a simple overhang on a building can truly drastically change the heat from solar gain into the windows. And you see here it changes it from 100 degrees on the wall to 80 degrees in the shade. So we look to our architect friends and our ownership partners to help inform design early on in the process, to look for opportunities to provide overhangs and to provide fins on the sides of the building, to provide forms of shading over the windows. When people think about energy efficient buildings, they generally gravitate towards thinking about the energy efficient equipment. But it's my opinion that the most efficient mechanical equipment is the one that operates the least. So work early in design with your energy modeling friends and mechanical engineers to help place these to reduce the heat load on your building. Similarly, building orientation can play a huge role with how much sunlight will be brought into your building. Again, it's great to work early on with energy modelers to just rotate building massing to help maximize views while minimizing solar heat gain into the building itself. Salt, it's what's at the ocean. You get salt spray, you've got salt life bumper stickers, you got saltwater taffy, but there is things near the ocean that are less a fan of it than we humans are. Common sight is metals and decay near coastal areas. Now, what really causes this decay at such a quicker rate? Well, let's look at the science behind rust. Anything that is exposed to water will oxidize. And this is a chemical reaction between dissolved oxygen within water and free electrons within metal. So the way to think about it is anytime metal is exposed to water, electrons will be lost, creating oxidation. Now, where does salt come into this equation? Well, salt is an electrolyte, and it's not just what plants crave, it's what electricity craves as well. Electrolytes dissolve in water to make an electrolytic solution, which just means that it makes the water conductive. And conductivity is really just the decreased resistance for electricity. Electricity is the movement of electrons. So by decreasing the resistance, we are increasing the amount of electrons that flow. So we are taking that standard reaction of electrons moving from metal to water and supercharging it. So what can we do for our building materials to help decrease this effect? Piggybacking off of Roger's point earlier, putting your equipment inside. Mechanical penthouses aren't just for showing off your awesome mechanical equipment to your building occupants. They're also great at protecting your mechanical equipment from being exposed to any salt air or adverse conditions that are outside. For items that can't be put in penthouses, say an exhaust fan for a grease hood or something like that, we recommend selecting equipment with materials that are more resistive. You can see here on the left, there's this chart at the top. It says active end, at the bottom it's passive end. All this is saying is that active end is more likely to lose electrons, passive end less likely to lose electrons. The further down you go, the more corrosion resistant. Engineers in the past, from time to time, have been accused of gold plating their designs. So we generally recommend stainless steel as a starting point for what material you should use. Eagle-eyed viewers will notice here that aluminum is a pretty common rust-resistant material, or a corrosion-resistant material, I should say, but it's pretty high up on the active end, meaning that it actually oxidizes pretty fast. And this is generally just because not all oxidation is created equal. Rust or iron oxide is the classic and typical flaky rust on an iron fence kind of look, grabbing it disintegrates in your hands. Aluminum oxide, on the other hand, actually is a hard, thin, passive corrosive material. So the outer layer of the aluminum will corrode and then create a layer of protection to stop further corrosion. So as long as you don't scrape it off, it'll remain protected for any future corrosion. For items that can't be made out of materials such as heat transfer, cooling coils and the like, the thing you can do is coat them. Common coating for these would be something like Blygold. It's a spray-on coating that's provided by manufacturers or third-party vendors. And these coatings are tested against ASTM B117, which is more commonly referred to as the salt spray test. Essentially, it's put in a lab and the coating is tested by spraying a salt fog against it with the ratings provided in hours at the end of that test. 1,000 hour salt spray, 5,000 hour salt spray, 10,000 hour salt spray. With the higher you go, the more resistive to corrosion that material is. So select based off of your expected life of that equipment, location, and those factors. Salt, it's not just in the water, it's not just in the air, it also permeates to the ground below. And as we've mentioned earlier from this list you can see on the left, everything will eventually corrode when it's exposed to salt water. So how can we stop something that is constantly under attack by being underground? Well, as we mentioned earlier, corrosion is really just the losing of electrons to the water. So if you're losing electrons, you just need to find something else that will give you more electrons. So for something like this, we have these stainless steel tanks. We provide what's called zinc anodes, which attach to our metal that we're trying to protect. These anodes will give up their electrons to our material we're trying to protect, and the anodes will actually corrode more than the material, in this case, steel. We do this in two different ways. We do this by a simple sacrificial anode system and an impressed current system. They essentially function the same way. The only difference between the impressed current system is that movement of electrons is regulated by a rectifier as mostly a gas pedal to just make sure we're only delivering the exact amount we need. Not terribly used in the built environment industry, more commonly used in pipeline applications. For most buildings that we see, we're going to namely just see the sacrificial anodes. Sweat. As a Southern California guy myself, it's probably my least favorite part about going to the beach. Usually more of a dry heat guy myself. So ASHRAE and IECC have put together the climate zone map, which essentially maps out what we intuitively know about the United States. You can see here that Arizona is hot and dry, while Miami down here in zone 1A is very hot and humid. But what does this all mean in terms of energy? What we have in front of us right here is called a psychrometric chart. If you've ever seen an engineer go a little bit cross-eyed, they may have spent a little too much time looking at one of these. But what this is really just showing is it's a plot of average temperatures throughout the year on a graph. And you can see here that Los Angeles, though the famous meteorologists, the Red Hot Chili Peppers, will tell you there's rarely a cold day, there's plenty of cool days. They usually range between 60 and 70 degrees with a relative humidity around 80%. Now, we've put a plot on here of 75 degrees and 50% relative humidity, dead center of the table, and that's generally a reference point for the indoor temperature conditions we're trying to maintain during a cooling conditions. So if we look at that dot, anything above that dot has to be dehumidified. Now anything to the right of that dot has to be cooled. So essentially anything in this green area needs to go through a cooling coil of some kind. Now, we've picked a point here, an average temperature day, and brought it down to 55 degrees, which is essentially the delivery temperature of most supply air systems. Now, I got into engineering for the fashion, not the math, but bear with me while we work through this. So looking at this movement at this point from an average day to 55 degrees, we can see that we have to take two portions of it, the latent load and the sensible load. The latent load is the dehumidifying and removing of moisture. The sensible load is the change in temperature, where it goes from, in this case, 80 to 55. And you can see based off of this, we require 27 BTUH to cool that air. Now, let's hop on a plane and head over to the east coast of Miami. Immediately, we can see that the temperature of Miami is both higher and has more water content, and it is much further away from the 75 degree, 50% relative humidity point we're trying to maintain. Now, getting at the chart, everything in this green area has to be cooled. So a majority of the year, we're having to cool this air in some way. And the line to get us from that average temperature to 55 degrees has grown greatly, with it going from 27 BTU to 83 BTU. But a key component of this actually is that you can see here from the sensible side, when we think of classically, why does it require more energy in these tropical climates to cool? We think, well, it's obviously because it's hotter, but it's actually only twice as much energy to cool the air in Miami versus Los Angeles for just the temperature. It's over quadruple for the latent to actually remove that moisture from the air. So when we're really thinking about these coastal and tropical climates, we really have to think about how much more energy is strictly from the outside air itself. And the numbers back it up. You can see here in comparison to a warm climate and a hot and very hot climate with humidity listed here on the right, you can see it's much greater. And this is a double whammy. Anyone that's living in Hawaii or down in the Caribbean can tell you, we're very lucky in the US that most of our electricity bills are between 8 and 14 cents a kilowatt. Back when I was living in Hawaii, it would not be uncommon to see mid 30 cents a kilowatt for my electricity bill. So that may have even grown. Well, what can we do about this? Well, for one, as we mentioned, we spent a lot of hard work cooling down that air to 75 degrees and 50% relative humidity in the space. And that air is going to be relieved from our building in some way, whether that is through exhaust fans serving restrooms or just simply from pressurization. Because if you bring in 5,000 cubic feet of something, it's got to be brought out and replaced eventually. So one way we can do that is running that exhaust or return airstream through what's called an energy recovery device, whether that be a wheel or a cube or a wraparound heat coil. It's just a means of passing the airstream of the exhaust against the outside airstream. And this is a way to passively cool and dehumidify your air without providing any sort of coil. You can see here in this example, you're bringing air from 95 degrees down to 80 and removing that moisture as well. A other way that you can reduce the outside air is be more precise and decouple your systems. You decouple your outside air ventilation from your actual cooling of the space itself, and then delivering that air precisely to the areas that need it. This is also the greater application of when you're doing a mixed air system, you inherently have to use a higher percentage of outside air just to meet the minimum. So also a good way to think about this is if you're in an office application where it's 70 degrees outside, but it's 90% relative humidity, you're going to have to run this DOAS to condition the air. But you may not have to run the indoor unit to condition the space. So going back again to the best piece of equipment from an energy efficiency perspective is the one that you operate the least. Finding ways to turn down equipment by shifting their usage is a great way to save energy. And you can get even more granular when it comes to outside air delivery to spaces with either occupancy sensors controlling dampers or demand control ventilation controlling to CO2. Ask your local friendly engineer. They will be happy to talk you through all of your options. Strong winds, pretty ubiquitous with hurricanes and tropical climates. And as a result, third-party agencies and testing procedures rise to meet these weather challenges of these locations. Miami-Dade has become essentially the industry standard for all building materials to include shingles, facades, mechanical systems installed in hurricane-prone regions. Other jurisdictions in hurricane-prone regions simply reference Miami-Dade County approvals to say if it's approved by Miami-Dade County for their hurricane region, you can install it in ours. On a more granular level, we also have testing procedures for other just simple items like louvers. You can see here we have the AMC testing for high velocity wind driven rain, and we also have testing for impact by windborne debris. And when I say impact testing, I truly do mean impact testing. The end result of all of these testing is actually essentially a potato cannon launching a 2x4 at a louver to test its resiliency against any sort of windborne debris. And after all of these tests and procedures and approvals, you'll get something like on the louver on the right, which you'll want to see, which you'll want to select when you're looking for materials in this region. You'll see the Miami-Dade County NOA, or Notice of Acceptance number, to say that it has been approved to be installed in their hurricane region, along with impact testing and their high velocity rain acceptance. As Roger said earlier, it's much less of an effect, but your louvers will generally have a lower free area than traditional louvers, where you will see generally 35 to 40% free area versus 55 to 60, which you may see with typical louvers. Now, outside of strong winds from hurricanes, there's usually a windward and a leadward side to buildings. What we have down here below is actually a wind study test on a building that we're working on down in the Cayman Islands. Now, these are pretty typical tests for structural engineers, actually. It's a way to define your structural materials and facade based off of the pressure from the winds faced in a certain direction. So this is mostly used for that application, but we can use these things to inform our design. So you can see here in the next slide, we have a typical study, the wind study test that was done for this building. And from that and historical data, we're able to see that the wind was generally coming from our site from northeasternly or easternly directions. So early on in design, we worked with the architects and the owners to, although the louvers will be rated for wind-driven rain, to try and minimize how much of that wind-driven rain they see. So based off of this, this wind test, we were able to put the louvers on either the westernly side or the southerly side of the building. It's just to show that you can use, you know, non-traditional design methods for multiple trades. All right, Roger, hand it back to you.
Thank you so much, Keith. So Keith took us out into the solar system. Part of my job here is to bring us back safely to Earth. So next slide. We're going to talk about shaking. And to do that, we need to talk a little bit about how the Earth is put together. And for the sake of this presentation, we're going to assume that it's not flat, but it is, in fact, spherical. One of my favorite books as a kid was Journey to the Center of the Earth, particularly the movie. And I'm not talking about the 2008 Brendan Fraser version. I'm talking about the 1959 James Mason Pat Boone version, based on the 1864 Jules Verne novel. Now that I'm older and know a little bit more about the planet, I see that it probably wasn't a very realistic story. If we were actually to take a journey to the center of the Earth, first of all, we'd need to walk in that direction, and we would need to travel 4,000 miles to get to the center. And in that 4,000-mile journey, only the first 60 miles of that journey would be through Earth, through the Earth's crust. After the 60th mile, you would be into the Earth's mantle, hot molten rock, eventually into liquid iron and nickel. And then at the very end of the journey, your last 75 miles of walking, you would need to carve into a solid iron nickel core. But we're not going to talk about all those parts. We're going to focus on that crust, or what is known as the lithosphere. Now, we think of this lithosphere, this Earth's crust, as a sort of solid object, but it's not. It's made up of 7 major tectonic plates and a couple of dozen minor tectonic plates that are constantly moving and shifting. Now, some of these plates are pretty stable. Most of them are pretty stable, but there's a handful of them that behave badly as of late. And those ones here are shown in color. The biggest one being the Pacific plate. That's one of the major plates, but also the Nazca plate, Caribbean plate, Cocos plate, Juan de Fuca plate, and the Philippine plate. These plates are still shifting on a regular basis. When we put these image together left to right, what you get is the ring of fire. So this area in red represents that map that I showed earlier. 95% of all earthquakes that have happened during my lifetime have happened within that red zone, within that ring of fire. Not to say earthquakes can't happen other locations. We know that in Washington, D.C., we had a pretty decent one a few years back, but most of them are in this general area. So when these earthquakes happen, they generally happen at some level below ground, and there can be butt plates, there can be slip plates. but pressure builds up and builds up. The land doesn't move until the pressure is such that there's a snap and the two plates suddenly shift against one another, and they produce two waves, a P wave and then an S wave. The P wave is a primary wave, S wave is a secondary wave. So next slide. So the primary wave, although it's a big wave, because it's not oscillating and doesn't have the long wavelength, it tends not to do that much damage. The real damage comes from that secondary wave and the harmonics of it, the wavelength, the up and down motion. That's what causes most of all the damage. So damage can be to roadways, to infrastructure, but this afternoon we're focusing on the buildings. Most of the injuries and deaths that happen within a building in an earthquake are a result of things falling on people's heads, ceilings, ductwork, piping, or equipment shifting and falling off of the buildings and hurting people below. One of these earthquakes happened not long ago. Keith was talking about the Cayman Islands. We do have a number of projects going on there. Back on January 10th of 2018, there was a pretty major earthquake that happened exactly at one of the junctures of these two plates, the Caribbean plate and the North American plate. The Cayman Islands is located literally within a couple hundred yards of that connection point. And when that earthquake happened, it rattled the island, caused a lot of damage, not only to the buildings, but to the ground itself. It created fissures. Those fissures changed the way that the water moves underneath the island, and some geothermal systems there were damaged as a result of that. So this image here is of the Hotel Indigo in Grand Cayman, a project we completed just about, 2 years ago. And in the design of this building, we had to take into account the high likelihood of future seismic events. So some of the steps taken to mitigate that: first, the ductwork within inside the building would not use the same kind of systems we would use in most other places. We had enhanced bracing and swing bracing for the ductwork to not only carry the load of the equipment, but also to keep the equipment from moving from side to side when that shaking occurs. Very similar supports were provided for the piping systems throughout the building. And then up on the roof of the building, all the major pieces of equipment are secured and held down by seismic equipment snubbers, literally holding the equipment down when those waves happen. We have seen instances where equipment has jumped off of the roof and landed below. So there is a lot of mechanical equipment typically on the roofs of buildings that have rotating equipment, and they require vibration isolation. But in the case of this project and other seismic projects, you need specialized vibration isolation, ones that will allow the equipment to vibrate, but will not allow the equipment to move too far to hold it back from an extreme condition. So the very last S, we're getting close to the end, is stack effect. And stack effect essentially is a phenomenon that happens when you have a building with one temperature inside and a different temperature outside. The taller the building happens to be, the more substantial the pressure difference and the stronger the internal forces become. So the image on the right-hand side is of the John Hancock building in Chicago. I lived there for a bunch of years, and it's closed now, but there was a really nice restaurant at the top of the building that my wife and I would go to. And when we would go there in the wintertime, you would immediately experience the stack effect. There would be days where it could be 0 degrees outside, and the inside of the building was kept at a nice, comfortable, 70, 72 degrees. And there would be individuals that would be there to help you open the door, because if you were to let it swing, you could damage the door. The forces were so strong that it was difficult to move the doors. And then as you walk towards the elevators, the elevator lobby, the noise would be incredible. The roaring sound of all the air from the lobby rushing into the elevator shafts and forcing its way up through the building. So a tremendous amount of air infiltrating at the lower levels of the building, and that same air exfiltrating at the top of the building. The energy impact to this in a place like Chicago could be enormous because you have so much unwanted air entering into the building, which now also needs to be heated to maintain thermal comfort in the space. That was designed by a company called SOM, very famous structural engineer by the name of Fazlur Khan. SOM also designed the Burj Khalifa project I am very familiar with. It took up 5 years of my life. It has exactly the opposite design challenge. It has what is known as negative or reverse stack effect. It is generally much hotter outside than inside, and that cooler air inside will try to drop down elevator shafts and stairwells and force its way out the bottom of the building, creating an exfiltration condition at the bottom and an infiltration condition at the top. And those impacts also need to be mitigated. So a little bit about the Burj Khalifa. Used to be called the Burj Dubai. They changed their name upon opening, but it is in the Guinness Book of World Records. It is, in fact, the tallest building and man-made structure in the world. It stands 828 meters tall, 2,717 feet, 163 floors. It has more than 900 residents living in the building. On a peak day, there will be more than 10,000 occupants in this single building. It is an office building, it's a hotel, it has retail stores, restaurants, and again, largely it's a residential building. So I recall on my first trip to Dubai, on the airplane, getting ready to land, I looked at the monitor at my seat, and it said the temperature is 48 degrees outside. And I said, oh, that sounds very mild. Till I realized it was 48 degrees Celsius or 118 degrees Fahrenheit. It was really hot and really humid. And the building, again, was designed to be very tall. To put it into perspective, it is more than twice the height of the Empire State Building. It's up there. So graphing these temperatures, though, through the course of the year, again, on a design day, 115 degrees outside, 72 degrees Fahrenheit inside, we have an extreme. We have an extreme difference of 43 degrees between in and out, and we have an extreme height. So it's probably the premier example of stack effect of buildings within the built environment. So when we started our design, we knew we were going to experience these forces. We made some assumptions. One thing that we had assumed was that we would have what is called a neutral pressure plane, meaning we knew the higher floors would infiltrate, the lower floors would exfiltrate, but we believed that the separation of those 2 points would happen at the midway point in the building at roughly floor 80. We were wrong. We did some computational fluid dynamic modeling and actually found that that neutral pressure plane happened lower in the buildings, down around floor 60. And we had to think a little bit more why this was happening within our model, and we figured it out. The next slide, part of it has to do with different air temperatures at different elevations. Again, a design day of 115 degrees Fahrenheit, as you're walking into the building's lobby, you take the elevator to the top, you get out, and the temperature is now down around 106 degrees. So there's about a 10-degree difference in temperature just based on being that much higher up in the air. The higher up you go, the cooler the air temperatures become. That had an impact on the models. Secondly, and probably more impactful, was air pressure. So air pressure on Earth at sea level is 14.7 psi. That's 144 pounds per square foot. As you go higher in the air, anybody on the phone who's ever climbed Mount Everest would know that the air is very thin. Well, it's not Mount Everest, but it's a half a mile up. At a half a mile up, the air pressure is only 13.7. So there's a 1 psi difference in air pressure. Does not sound like a lot, but 144 pounds per square foot. If I had a piece of glass that was 8 foot by 4 foot, you'd find that the additional pressure on that glass is about 4,000 pounds of horizontal pressure being put on one side of that glass. Next slide. So when we plotted out then this stack effect measured in CFM, cubic feet per minute, again, infiltrating into the building at the upper levels and then exfiltrating at the bottom. This is what the graph looks like. And you'll notice that the extreme condition actually happens at the first floor. Reason for that is this is where the building's outside doors are, and much more difficult to control. So the air is leaving the building at that floor at a much greater rate than the other floors. But we have a lot of openings in the building, and even at some of the highest levels in the building where there's residents, there's balconies and balcony doors and lots of places for air to be pushed into the building. So we need to take steps to mitigate it. There's all kinds of bad things that can happen with forces that are this strong. Doors can be taken off of hinges, louvers can be damaged. The building's facade can actually crack, become damaged. So some of the things that can be done or were done on this project, providing air exhaust and intake measuring stations at every zone, providing differential sensing devices to measure indoor and outdoor pressure at every zone, and then increasing the outdoor air volume into certain zones to help to equalize that pressure. And then avoid, to the best we could, continuous stairs and elevator shafts. There's a lot of breaks in the stair shafts and breaks in the elevator shafts, although there are also express elevators that take you to the top. Some other things, or one important thing that I would recommend for any tall building is that the elevator lobbies be provided with vestibules. These vestibules do a great job in breaking up that stack effect. And then again, for this building, near the top of the building, a lot of it is residential. You have people with apartments and balconies, and they like to go outside and enjoy the views, enjoy the somewhat cooler temperatures. But technology was used inside the residential units that would have limits on it. If the outside wind speeds were too strong, it would lock the door. It would prevent you from going outside. Going outside could be hazardous, be blown off your balcony. It would also include nuisance alarms. And what this would do is it would be possible for an occupant to open up the door to their balcony. It would also be possible for them to open up the door to the lobby from their unit. But if you were to open up both doors at the same time, a very loud, annoying alarm would go off. That would tell you you really can't or shouldn't be doing both, because that would have a huge impact on the amount of stack effect that would happen. That cold air would rush in, or that cooler air would rush into the building and down the shafts and aggravate the situation. Next slide. So that's with the Burj Khalifa, a half-mile tall. It is the tallest building, but it won't be for long. There are a lot of other very super tall and mega tall buildings that are being contemplated around the world. And the taller you go, the more critical the issue of stack effect control will be, and technologies will need to be created and evolve to be able to sort of deal with those natural forces. One last image from the observation deck at Burj Khalifa, but that is the 8 S's. So we hope you've picked up something from today's discussion. We're thankful that you spent the time with us. And now if there's any questions on our list here, we can go through them. Keith, do we have any questions?
It doesn't look like we have any questions that Alexandra has answered already, but if you guys have any questions, as Alexandra said, after this course, just send them to us and we'll be happy to respond.
Yeah, I did see that someone asked the question whether the deck would be available. The presentation is being recorded and it will be available on the Interface Engineering YouTube station for anybody to. It usually takes us a couple weeks to get it up there, but you would be able to go there and watch the presentation as many times as you'd like.
And you should also be able to download the slides directly from the website. But if you have trouble with that, I've written my email in the little answer field of the questions, and you can send me a direct message and I'll get it to you. Okay, yeah, so our next thing is definitely keep a lookout for our next webinar on July 24th for doing the balance between lighting design and sustainability. I have heard that this is a good one. She's given it a few times to a variety of audiences, so you should be getting a link in the next week or so to register for that one. Thank you all so much for participating today. We hope it was informative. If you have any suggestions for improvements or requests, suggestions for future topics, also we're always looking for that. Yeah, that's about it. Thank you so much. Enjoy the rest of your day.